The automotive sector is currently experiencing a profound paradigm shift, driven by a convergence of technological advancements and changing market dynamics. This period extends beyond typical product cycle updates, challenging the fundamental structures that have defined vehicle manufacturing for over a century. The core inquiry centers on whether the established industry frameworks can adequately adapt, or if this confluence of forces will necessitate a complete re-architecture of business models, engineering priorities, and supply chain dependencies, ultimately redefining the very identity of an automotive enterprise. It is a transition from incremental innovation to systemic transformation. Historically, the automotive industry thrived on a deeply specialized, tiered supplier network, where original equipment manufacturers, or OEMs, served as final integrators. Vehicle development cycles were characterized by lengthy, hardware-intensive processes, meticulously refining internal combustion engines, chassis dynamics, and passive safety systems. This model fostered deep expertise in mechanical engineering and mass production efficiency but inherently limited the pace of cross-functional innovation and software integration, leading to rigid architectural limitations and extended time to market for significant changes. The introduction of electric powertrains initiated the first major disruption. While ostensibly simplifying the mechanical drivetrain by replacing complex multi-component engines and transmissions with electric motors and reduction gears, this simplification introduced an entirely new layer of system complexity. The fundamental challenge shifted to high-voltage battery management systems, sophisticated thermal regulation for optimal cell performance, intricate energy recuperation strategies, and the integration of robust charging interfaces, requiring expertise in power electronics and electrochemistry previously less central to automotive design. Battery technology remains the singular most critical determinant for electric vehicle adoption, dictating range, charging speed, and overall vehicle cost. Current lithium-ion chemistries present inherent engineering trade-offs. Maximizing energy density often compromises power output or cycle life, while improving thermal stability adds weight and complexity. Furthermore, the reliance on specific raw materials like lithium, cobalt, and nickel introduces significant geopolitical and economic dependencies, creating a critical challenge for sustainable, large-scale production and recycling infrastructure. Advances in solid-state or alternative chemistries, though promising, are still years from widespread commercial viability. Concurrently, the vehicle is evolving into a sophisticated, software-defined platform. This transition moves beyond isolated electronic control units to a centralized computing architecture, where complex algorithms manage propulsion, chassis dynamics, advanced driver assistance systems, and an expansive infotainment suite. This transformation necessitates integrating tens of millions of lines of code, managing intricate data flows, ensuring real-time performance across diverse sensor arrays, and establishing robust cybersecurity protocols to protect against external vulnerabilities and maintain system integrity. The advent of software-defined vehicles enables over-the-air, or OTA, updates, a capability that fundamentally redefines the product lifecycle and the relationship between manufacturer and customer. Vehicle functionality, performance characteristics, and new features can be deployed or modified post-purchase, transforming a static product into an evolving service model. This introduces challenges in continuous software validation, global regulatory compliance for dynamic feature sets, and the management of potential system vulnerabilities, while simultaneously opening avenues for new revenue streams through subscription services and feature upgrades. Manufacturing processes are also undergoing radical re-engineering, exemplified by innovations such as Gigacasting. This method consolidates dozens of traditional stamped and welded sheet metal parts into a single, massive aluminum casting, drastically reducing the component count, assembly time, and production costs for vehicle structural elements. However, implementing gigacasting demands substantial upfront capital investment in specialized machinery, expertise in advanced materials science and metallurgy, and a complete reimagining of factory layouts and automation sequences, fundamentally altering established body-in-white manufacturing workflows and supplier relationships. The traditional automotive supply chain, meticulously optimized for combustion engine components and fossil fuels, faces an unprecedented need for restructuring. Sourcing critical raw materials for batteries and power electronics, such as rare earth elements and specialized semiconductors, introduces new geopolitical and economic complexities. Establishing resilient and diversified supply networks, particularly given the concentrated geographical distribution of mining, refining, and manufacturing operations for these materials, has become a strategic imperative, influencing national economic security and global trade policies. In response to these supply chain pressures and the drive for differentiation, many OEMs are increasingly pursuing vertical integration. This strategy involves bringing the design and production of key components, like battery cells, electric motors, and proprietary software, in-house, rather than relying solely on external suppliers. While this aims to secure supply, enhance control over intellectual property, and enable deeper product differentiation, it requires immense internal investment in research and development, manufacturing capabilities, and talent acquisition, often challenging the established asset-light strategies. The competitive landscape is expanding significantly beyond the historical incumbents. Technology companies, renowned for their agile software development, rapid iteration cycles, and deep understanding of consumer electronics and user interfaces, are actively entering the vehicle manufacturing space. These new entrants often approach vehicle design from a software-first perspective, prioritizing digital experience, connectivity, and data integration, directly challenging the established automakers' engineering-centric development methodologies and long-standing risk-averse corporate cultures. This convergence of electrification, software, and advanced manufacturing creates a critical talent gap across the industry. The demand for highly specialized software engineers, artificial intelligence and machine learning experts, data scientists, and electrochemists far outstrips the traditional automotive workforce, which has historically prioritized mechanical, electrical, and industrial engineering disciplines. Attracting and retaining this new generation of talent, alongside retraining the existing workforce, has become a formidable challenge, impacting innovation speed and project execution. Modern vehicles are increasingly sophisticated data collection platforms, generating vast quantities of telemetry, sensor data from advanced driver assistance systems, and user interaction logs. The management and utilization of this immense dataset raise complex ethical and legal questions regarding data ownership, individual privacy, cybersecurity vulnerabilities, and the responsible deployment of autonomous functionalities. Developing robust regulatory frameworks that balance innovation with consumer protection and national security remains a significant legislative hurdle, often lagging behind technological advancements. The widespread adoption of electric mobility necessitates a dramatic expansion and intelligent management of charging infrastructure. This extends beyond merely installing more charging points. It requires the development of smart grid integration capabilities, potentially leveraging vehicle-to-grid, or V2G, technology for grid stabilization and energy arbitrage. These infrastructure demands present substantial investment requirements, complex electrical engineering challenges, and new cybersecurity considerations for protecting interconnected energy systems. International regulations and safety standards, historically developed over decades for combustion engine vehicles, are now struggling to keep pace with rapid technological evolution. New protocols are required for high-voltage battery safety, autonomous driving system validation, and data privacy compliance across diverse jurisdictions. The lack of harmonized global standards risks fragmenting markets, increasing development costs, and complicating the global deployment of advanced vehicle technologies, potentially hindering universal adoption and economic scalability. In summary, the automotive industry is not simply experiencing an iterative upgrade cycle. The confluence of electric propulsion, pervasive software integration, transformative manufacturing processes like gigacasting, and a fundamental reevaluation of global supply chains represents a structural reshaping of the entire sector. This dynamic interaction of forces demands a complete reassessment of core competencies, investment strategies, and competitive positioning, fundamentally altering the value proposition and operational models that will define automotive success for decades to come.